Hi, ladies and gentlemen. Today we will be discussing on how to apply Mohr circle into stress orientation calculation. My name is Julapot Jiravacharadet. This discussion is a part of a lecture of Mechanics of Materials, a taught course in International Program in Civil Engineering at King Mongkut University of Technology, Thonburi. In general, we look at the stress in a plane that we are familiar with. We talk about normal stresses, or sometimes we call axial stress so far, in the x or y direction, whereas the shear stress tau, we tend to look at a vertical or horizontal direction as well. So it's something that we're familiar with, right? A horizontal line, vertical line. However, when we actually done some tests and work on materials a lot, we realize that maybe the failure is not the way we think it is. For example, if you test a beam and it fell in the shear dominated region, what happens is it's not really going vertically, right? It's a some angle tend to be something like about 45 degrees. Similarly, if we do the compression test in a concrete, there's a failure mode, a shear failure mode. There is also a line, diagonally, something like about 45 degrees as well. So it makes us come to think maybe the mechanics of material doesn't actually go in the line of orientation we are used to. So to cope with such phenomena, what happened is that from the orientation we are used to, because this orientation, although we draw it as a box, actually we actually consider a very small point in a structure per se. Notice that there is no change between the left and right or up down value of the stresses. That is because we consider this is so small, there is no size in here, right? So it happened that maybe we can look at the same point but with a different orientation. For example, if rather than looking at horizontal and vertical, what happened if we look at the orientation that kind of turning like anti-clockwise in a degree of theta, right? And from that on, then with a lot of proof, then we can actually work out the equation for this sigma x prime and tau x prime y prime, which is a more general term. It's not in the x or horizontal or y vertical anymore. It's x prime y prime in a sense that it could turn in any angle, right? And this is because this lecture is about how we use the Mohr circle. So I will just stop here because we need to make certain, I want to make certain statement or observation for this one. However, I will provide proof in the part 2 of the Mohr circle theory. Right. Before we move on, I have to emphasize on the fact that for this proof, which I based on a textbook which was given already in the handout. So this is the positive direction. I have to mention this because there are different proof, right? Different textbook prove it in a different way using different notation. So for this one particularly, we use this sign as a positive direction, and we turn this box around to match the stress direction that we want. But I will show the example later on, right? But in this case, remind this for now. And before we move on, I want to make an observation because something that's a key point why I stop here. The first observation that we will have to carry on to the next stage is that if we rotate the element or change the orientation of element physically by 1 theta, the equation shows that the stresses are affected by 2 theta, meaning we turn 1, the equation become 2, cosine 2, sine 2, right? Degree, for example. Right? So this is something that we have to take bear in mind when we use and thinking about this orientation of the elements and the stress value that associated with them. Secondly, because of the changes in this way, cosine and sine go in a circle, right? It comes from circular function. So basically, there must be some maximum and minimum value of stresses somewhere. Right? It might not be exactly x or y, it should be x prime y prime, or sometimes it might be xy, we don't know. But anyway, there must be changing, and then there must be a max and min in this graph. And because sine and cosine go in a circle, it means that the stress value will repeat itself if you rotate this element when the 2 theta become 360 degree, right? Because that's where it repeats the circle. Or in a way, for the stress level, it means that when theta, when you turn the element by 180 degree, right? And this is why, notice the opposite side of the stresses, the value are the same number, right? Sigma x and sigma x, sigma y and sigma y are 180 degree from each other. And since we are in that sense, the stress in the x and y are actually, because x and y are 90 degree different, therefore the 2 theta in stresses value will be 180 degree different. That again, I have to mark this because there will be some kind of consequences in how we apply the Mohr circle, which are proved after this. Right? If we maintain the beginning equation and then look at them, they realize that this actually can form some kind of equation that can relate between sigma x prime and tau x prime y prime. So we rearrange the equation, and it can be shown again. I will prove in detail later on in part 2, but we can form in this kind of equation, right? If you think that look kind of familiar, it is actually, well, because it is. If you look at the standard form for circle equation, this is when we plot x and y, right? So this is standard form, and the origin is x naught and y naught, right? So if we compare the standard form of circle equation and what we have for sigma x prime and tau x prime y prime, it just simply means that if we plot a graph between the value of sigma x prime on basically the normal stress and the shear stress when we go around in a circle, in the whole loop, then we get a picture of a circle, right? And for this calculation, we're going to use this circle, and this circle is what we call Mohr circle. Here are example on the whole total idea of how we look at Mohr circle, right? Notice that I put in colors, right? Actually, it comes the fact that when we started off, we have a pair of sigma x, tau x, xy, right? Then we can plot on the graph. In this one here, because the manipulation of how we rotate the element, the textbook I reference is actually put tau positive downwards and normal stress, shear stress downward positive, and normal stress to the right hand side positive, right? So when we turn element, the stress plane, the stress line will turn the same way. Otherwise, it might turn differently depending on the textbook you use. But this one here, it will turn the same way. Now, if we plot a point, right, onto this graph, sigma x normal, the horizontal component and the shear value, and the other pair will be sigma y and tau xy, right? We have 2 points, right? The blue point, if you can see on this diagram, right? Now, because x and y are 90 degree different, this is what I already mentioned already, meaning that these 2 points is 180 degree different, right? In the stress term, meaning in the graph, because the graph we plot the stresses value. What does it mean? In fact, it means that the sigma x dot, the point of sigma x and the point of sigma y is on the opposite side of the circle, right? This small circle, which means that if we connect this line, because it's on the opposite side of the circle, when we connect this line, you see the blue line, the blue straight line, right? Then it means that is the diameter, right? And at the middle of the diameter is the center of a circle. In this case, I mark point O, right? Because the height of tau x minus x tau xy and the bottom one of the tau xy is equal, so it's halfway at cut tau equals 0. And then once we know that, we can then draw a circle. And you need to notice the circle, because it go in a circle, then it appears that on the most right hand side, we have sigma 1. I denote sigma 1 because that's the normal thing they use. Sigma 1 is the highest normal stress you can have on this diagram, right? Because don't forget, your sigma has to be lying in this circle. Sigma and tau, any pair will lie on this blue circle, right? So on the most right hand side then become the maximum normal stress that they actually call maximum principal stress. It notates sigma 1, right? This is a normal stress, right? And the most left hand side, right, then that is the lowest value. Then it becomes minimum principal stress. When I said lowest or highest, I'm talking about mathematical sense, plus minus count, right? But you know that in engineering, plus minus actually doesn't mean more or less. So you have to understand that what we are talking now is a kind of mathematical language. Minus is always less than plus. But in engineering, you will have to re-examine which one is bigger when you actually apply into your own work, right? So be careful on this one. But however, I will stick with the common normal notation. Positive is max, negative is min, right? So in this case, sigma 2, then on most left-hand side become the smallest value of normal stress you can have, and it's called minimum principal stress, right? And of course, the maximum tau, because of the symmetry up down of this graph, it means that the maximum and minimum will be the same number, just plus minus, right? And it's called maximum in plane shear stress, sometimes called maximum shear stress in short, right? So this is the whole thing we need. And every time we turn this, we want to know any of this element, then we turn this blue line, the straight blue line, to the angle we want, right? And then we calculate the value of the stress and both normal and shear using this circle. Well, it might need some imagination to see how it goes, but we will see example right now of what I mean. Okay, let's look at this example, right? This is the element was given by our normal orientation that we tend to calculate things to begin off with, right? It's in a horizontal and vertical orientation that we are familiar with. However, as we already learned, that this might not be the state that caused the problem. The state that caused problem might be in different orientation. So what we want to know is that the first one, we were tasked with three things together. First, we have to identify what is the maximum and the minimum principal stress, and then draw the element in that orientation. Right. The second one, similar, but this time is the orientation that show the maximum and minimum shear stresses. And the third one is what happened if we turn this element by 10 degree anti-clockwise. What would be the state of stresses, right? And we will again have to draw that picture, or the state of the stress states in this element in that orientation. Before we begin the calculation, I will start off with the initial setup, which I tend to call step 0, because it's before question 1 or 2 or 3. It is something that every time we gonna do more circle, we should start here, begin here. First, we set up the axis. I repeat myself, that as I already said, for this proof or for this method, right, we will set up shear stress downward positive, right? Because the question give unit in megapascal, so the axis, the distance we measure here is in megapascal as well, right? And the horizontal line, right, which is normal stress. Notice that I start to move away from axial and then using normal, because it's no longer always axial, but it's just normal, which means 90 degree to where we cut it, right? So basically, this will be normal stresses, and the right hand side is positive, right? The left hand side, the graph is negative. Now, again, before we start plotting, then we look at how we actually reference. This is our positive reference. Notice that sigma x is tension, right? Also the sign convention for positive. Therefore, the point A will have positive normal stress. However, notice the sign of shear. the 15 megapascal going down, coming down, whereas the positive sign saying it has to go up, right? Therefore, the tau is a negative 15. However, because the way we plot the graph, downward positive, therefore minus 15 is on the top there, right? Once we identify the first point, then the second point we use sigma y, right? There. Then we rotate our reference box, right, to match the phase of the sigma y. In this case, it happened that sigma y is compression, which is go against normal that we say positive, right? Therefore, it becomes minus 20 for the first coordinate. However, the shear this time, both going to the left-hand side, both the real stress, the real shear stress, and our reference, indicate that it must be positive, right? And from then on, what happened is that we can connect these two lines, again, opposite the circle. Once we have this opposite the circle, this line, this is diameter. At the middle, I mark point O, is then the center of the circle, right? You notice there's a formation of a triangle happening here, O, A, and C, right? I mark the height there and I mark the base there, which actually come from the coordinate of comparing coordinate between O, A, and OA, right? Therefore, we know the height, we know the base. We can use Pythagoras then to calculate the radius, right, which is OA, the side OA, right? Use normal Pythagoras, and then again using normal trigonometry, we can also work out of the angle alpha, right? But don't forget that this alpha here, although is happening here at 26 something, right? Then when you think about the element will return only half that. Again, I repeat myself. If it happened with the physical 1 theta, it happened in the stress plane 2 theta. In other words, if it happened in stress plane alpha, then it happened in the physical plane alpha, half an alpha, right? So this is something that we should remember before we move on. Now, then we go to the next step. When look at the maximum and minimum principal stress, I did not actually get into detail because it's quite a simple calculation. What happened is that, remember the blue line. The blue line is the original sigma x, tau x, xy, and then sigma y, and then tau xy, right? Then if we want to go to the maximum principal stress, what happened is that we have to rotate these two lines until this actually matching the horizontal line, correct? Meaning you have to turn this line clockwise by 26 something degree that we already discussed, right? Then we have sigma 1. Now the magnitude of sigma 1, the coordinate of point D, right? Tau is 0, as the picture already suggests. Then from the origin of the graph to point O is already 10, right? And then from point O to point D is again from the center of the circle to a point on a circle. Therefore, it is equal to the radius. Therefore, the coordinate of sigma 1, maximum principal stress, is equal to the 10 plus the radius, which work out to be 43 point something that I mark in the picture. To calculate sigma 2 is the same thing, right? Then it will be coordinate of sigma 2, right? The radius actually from between point O to point E. However, point E is already on the left to the right hand side of 10, and then move the other one to the left hand side equal to the radius, therefore it becomes 10 minus r, right? And then work out to be 23 something. Again, the shear is 0, right? But the element itself, as we already discussed, it is only half that, right? So if the angle in the stress plane is equal to 26 something, therefore, meaning we already turned the element by 13 degrees something, right? So to match that stress and the physical plane. And that's done. That's the answer for the maximum and minimum principal stress orientation. Next, we'll look at the orientation for the maximum and minimum shear stress, right? Again, we already discussed that the maximum shear, which is this time is the vertical axis, right? The maximum shear will be the lowest point because positive is down here, whereas the minimum will be up there at the highest, well, it is the same value, and it's just plus minus, right? Notice that the radius, right, it is from point O to the one below, which is point F or F. That is again from the center to a point on the circle. Therefore, that height equal to the radius itself. Therefore, meaning tau max is plus minus the radius. In this case is 33 something there, right? Now, notice one thing though, it is something that I have to say here. This time here, the normal stress is not zero for this case, right? Because it's to go to the top, to the highest and lowest of the circle, you must measure exactly on the same level or in the line with the center of the circle, right? Which in this case, then it means that for normal stress, it already carry a unit of 10 megapascal, right? But positive though, okay? And if we compare to our standard reference, positive for normal actually means it going tension, right? We running out of the element, right? Therefore, we have the sigma both on four phases equal to 10, right? And then of course the maximum and the minimum shear stress is 33 equal to the radius 33.54 megapascal, right? And that's done. And the picture is drawn on the left hand side, as you can see in the brown, right? And that's done for the maximum and minimum shear stresses. The last part is we should show what happened to stress if we turn it by 10 degrees, right? I like in this picture here in general, I like you guys to focus on the purple color, right? On the left hand side, I already draw the element that I return 10 degrees with the pre-calculated version of the value of stresses. I will explain how to now, right? Don't forget that if we turn the physical by 1 theta, it happened with the stress through the equation 2 theta. Meaning if I turn this element by 10 degrees, I have to turn the line, the original line, by 20 degrees, which is shown that when I beginning x and y, we have the blue line, right? If we're going to turn the element by 10 degrees, then we have to turn that blue line also 20 degrees twice, two times, right? And once we go to that state, just to separate the color, just to separate them, I use the purple color here, right? And notice that I mark point G and point H, right? Because from A is sigma, if you remember, A is sigma x. When it turns to G, therefore it naturally it's just moving from x to x prime according to its movement, right? So that one coordinate will be sigma x prime and then tau x prime y prime, right? The original, the basic one, right? Don't worry about plus minus as yet because the calculation will show it later whether it's plus or minus, which we have to consider, of course. Then point B, which is actually at first sigma y, right? And minus tau x prime y prime. When it turn, then it naturally should be sigma x prime, right? So that's why I denote it that way. Now for the calculation, again we use a triangle, right? Notice that it's from the same way it's from a triangle downwards, right? The same as the triangle O, A, and C. If you draw the purple line downwards to done, then we have the another triangle. Just to make the picture less confusing, I didn't draw that line, right? But in a way, then from that one we can calculate sigma x prime. Because the coordinate, if we draw it down, the first one is 10, right, from the origin, point O, and then we add in the cosine. In this time here is the two angles combined, 26 original, and then we rotate it more, 20, then it becomes 46.57 degree, right? And from that calculation, we can determine what is sigma x prime. Tau x prime y prime is how, if we know that it's on the top of the circle of the axis, and on the top, shear stress is negative as we set up. And if we take that onto the opposite side of the angle, we use sine rather than cosine. And then we have the calculation and we put in minus because we know it minus on the top there, right? And that calculation gives you tau x prime y prime. right? For sigma y, then it's opposite side to left hand side to sigma x prime, right? Again, it go to right hand side for 10 because it's moved with the origin first, and then the radius with the time cosine is to the left hand side, it becomes minus, right? And that calculation will give you sigma y prime, and of course the one that attached the shear stress attached to it will be negative of what actually attached to sigma x. In this case, from negative because what attached to x is negative tau. Therefore, in with the sigma y prime, it is actually a positive shear stress, right? And that is drawn again compared to our common reference, right? So we have seen picture on the left hand side with the calculated value attached to it. And that is actually all for today. Thank you very much. I hope you enjoyed the lesson, and I hope it's really beneficial to you. And I hope to see you again next time. Take care now. Bye bye.